Hello everyone, this is Brock Skaggs, and in this video we're going to take a look at a transmission key found in a brush hog. And so got a few images here to kind of kick the problem off. Top left we've got a tractor, a 1960 Ford 601 tractor that we call Ginger, and on the back end we've got the brush hog here. And so we're looking to replace the key in the brush hog. And so if you're not familiar with brush hog, it's basically a big old mower. And so underneath the deck here, you've got this big plate that I've been told is called a stump jumper, and you've got the two blades sticking off of it here. And so if you look under the deck, after you've removed this, you've got this shaft coming down. And so in the shaft, you've got this milled key seat, and then also in the stump jumper, you've got this nice keyway that matches up with. And so of course the idea is you go and buy key stock of the correct size coming in from the store looking like something like this. You cut it to the correct length. You stick it in the key seat here. It also fits into the keyway here. And so then when the shaft turns, obviously it's able to turn the stump jumper and turn the blades and of course knock down your brush. And so the idea is, well, if I know some things about the brush hog, the PTO of the tractor, and some stuff about the key geometry, can I figure out what the shear stress is experienced by the key itself? And so that'll be what we're looking at in the problem. And so to give us some numbers to play with here, I'm looking up the PTO power output is roughly around 30 horsepower for the tractor. I'm assuming that the shaft on the brush hog is spinning at a roughly 775 RPMs. The shaft diameter, which is this diameter right here, is roughly 1.75 inches. The key cross section here, you can see it's a square cross section, so each side length is 1/4 of an inch. And I'm going to say the key length is 1.25 inches. And so this, of course, showing just the raw key stock, and then I cut a 1.25 inch section off of it. And so the task is now, okay, with that information, can I calculate the shear stress experienced by the key itself if these conditions are correct? And so let's first do a little bit of thinking about how this problem sets up. And so here I'll just make a brief image here. And so this will be a very simplified view of this key and the stump jumper, we'll say, that big steel plate that the blades are attached to. And so let's say that smaller circle there is the shaft, and this bigger circle represents that big stump jumper plate. And then what connects them that's able to transmit the torque is our key. And so we'll just draw a key right about here, just like so. And so the idea is, okay, let's say the shaft of the brush hog is wanting to turn in this direction, so in the clockwise direction. Well, that means on the very bottom surface of the key, it's going to feel a force that's trying to push it off to the right there. Well, on the top side, you're going to have at least the inertia associated with the big old steel stump jumper plate and the blade itself. If it's in operation, you're going to feel all the effects of it hitting stuff, weeds, tall grass, possibly small tree saplings, and everything else that you've possibly run over. And it's going to feel this force going off to the right here, or excuse me, off to the left there on the top side of the key. And so if I draw a key down here below, we can start to see this shear stress set up. And so say there's the key cross section, here's the length of the key itself, just like so. And so what's going to happen is right in the midplane of this key, so right on this surface that I'm trying to outline in blue, which we'll say is right in the middle of it, we're going to have these shearing effects felt here. And so basically you'll have, for us on the very bottom edge of that surface, we're going to have a force going this way. We've got a resisting force going on the top. You can see those forces are in parallel with the plane of the area itself. And so hopefully that's keying you off to thinking, well, hey, there's going to be some shear stresses, tau, and It's a direct shear stress application, so our formula is just like so. The force over the area in shear, where this force would be the magnitude of these shearing forces trying to shear the key in half along that plane. And the area in shear would be the area that I've shaded there. And so just knowing some things about the geometry of the key, well, this length here we'll call W. That's the 1/4 inch square side length. And this here would just be the length of the key here. And so that's going to be, the area and shear would be the product of those two values. So that's fairly easy. But what about the force? If I look up in my inputs, I'm not given any forces at all, right? I'm given a power and horsepower and angular velocity in RPMs. And really that's the closest thing as I have to a force. And so we have to start thinking about this a little bit. And so one of the things we can do is go from this power and angular velocity to the amount of torque that the shaft is trying to transmit to the stump jumper through the key. And then from the torque, well, we should be able to relate torque to force, right? T is R crossed F if we're just thinking of vectors there in general. And so that'll be our route to go. We'll take the power and the angular velocity, we'll get our torque. From the torque, we'll get the force. And then after we have the force and the area and shear defined, we can calculate our shear stress experienced by the key. And so let's jump right into that. And so first things first, how do we connect power, torque, and angular velocity? Well, in our reference here, it's found in chapter 4, the formula we're looking at. And the formula is P is equal to Tn all over 63,000 for this type of problem. I say for this type of problem because the 63,000 is just a conversion factor. In order for that to all work out, this P here has to be in horsepower, the T here has to be in units of inch-pounds, and the N has to be in units of RPMs for the angular velocity in order for that 63,000 to work out. And looking back at our units, that's exactly what we have, right? Power is in horsepower. The angular velocity of that shaft is in RPMs, and so now I can solve for the T value, and it'll come out in inch-pounds there. And so you just have to always be careful of our units here. And so let's go ahead and do that right here. T is going to equal what? P times the 63,000 unit conversion factor all over the angular velocity N. And so P we said was 30 horsepower times that big conversion factor, 63,000. And then we're dividing it by the angular velocity of the shaft, which we're saying is turning at this instant at 775 RPMs. And so let's slide over here a little bit and see if we can get a value for that. And so 30 horsepower times 63,000 divided by our 775 RPMs. I'm getting roughly 2,438.7 units here are in inch-pounds. So getting close to 2,500 inch-pounds. And so that's the torque. But again, we're seeing our home formula, our final formula is going to be tau is force over area and shear. Well, torque is not force, right? And so we've got to take this torque value and figure out the force itself. And so thinking back to kind of very base general definitions, we've got a definition that torque is always equal to R crossed F we could deal with if we wanted to play with vectors and the cross product there. Or, this is a little bit more simplified, I'm just interested in the scalar magnitudes of these vectors. One way to look at it is T is R perpendicular F, right, where we know that the position vector, or the position R, if I draw a line from the point of rotation that the torque's about to the line of action to the force F, I've got to have this perpendicular relationship here, which should be able to work for us in this application. And so if I slide back over to my simplified image here, it's almost as if I'm underneath the brush hog looking up at the shaft, the key, and the stump jumper with, of course, the blades coming off of it here. Well, the point of rotation, the point of application of that torque is right here in the middle of the shaft. Here are the forces we're trying to get a magnitude of. Well, the perpendicular distance would just be this vertical distance here, also known as the radius of the shaft there. And so we should be able to use that in order to get us to the force. And so with that being said, I can solve this formula for the force. Well, force here is T over R perpendicular, just using some algebra here. We said that R perpendicular, well, that's just going to be the radius of the shaft, or I'll call it D over 2, where I'm using the diameter of the shaft. And so this would come up to 2T over D, and now I'm ready to start substituting some values. So 2 times T, that was the torque that we were trying to transmute through this connection. I've already got the value right there in the top right, 2,438.7, that'd be in inch-pounds. And our diameter here, what did we say was the diameter? Shaft diameter is 1.75 inches. There's that. You can see my inches, my unit of length crossing off, which is very nice. Leaving with a force unit of pounds. You can catch a lot of errors in your work if you just keep track of units. And so this is roughly 2,787.1 pounds here. And so what is this? Well, this is the shearing force experienced by the key itself. This is the actual F value that we're hunting for in our shear stress equation. And so now we can solve for shear stress. I'm just going to rewrite that up here. Tau is force over area and shear. We've already got a good handle on the force. Well, how about the area and shear? Well, that's just going to be the width of the key times the length of the key. And so we are on our way. So the force, 2,787.1 pounds here. The width of the key, that's just the 1/4 inch square side length here. The length, we cut that key stock off and we said the length was 1.25 inches. Another way to work these types of problems is a design-oriented problem where you'd have to figure out what the acceptable length would be. But here we're just doing analysis, so we're given all the geometry and we're just saying, hey, what's the shear stress? And so computing this value should get us that. So 2787.1 divided by the product of 0.25 and 1.25. I'm arriving at 8,900, and we'll say it's 19, rounding it to the nearest unit. 8,900, excuse me, yes, and 19 units here, pounds per square inch, and so PSI right here. And so that is the result that we were looking for. And so determine the shear stress experienced by the key. We would say the shear stress experienced by the key is approximately 8,919 PSI there. And so that should conclude our problem. Again, just to recap, we're looking at determining the shear stress experienced by the key in this kind of transmission area where we've got the shaft, vertical shaft of the brush hog coming down to the large steel plate, I believe called the stump jumper, which then goes out to the blades itself here. And so what we've done is we went and we knew a little bit about the power that was trying to be transmitted through the system here, as well as the angular velocity of that shaft itself there. And from that we were first able to arrive at the torque, and then we used our knowledge of the relationship between torque or moments and forces in order to come up with the shearing force. And then we looked at the actual forces being applied to the key itself, noted that the forces are acting inside the plane of the area of the material of the key itself here, and so that's where we've got that shaded area of the kind of midway plane between the key itself where those shearing effects are going to happen, and the forces are acting parallel to that plane, so that's shear stress. Notice I'm using tau here and not sigma. And we know that the equation for this type of shear stress is the force divided by that area and shear. And so we figured out the force. Simple geometry tells us what the area and shear is going to be, and we've got a value of roughly 8,919 psi for our shear stress. Again, thank you for watching the video, and hopefully this helps you understand shear stresses and keys.